Okay, let's go back to the idea of comparing two independent means, and this time I want to take a look at a non-parametric technique. The idea here is what happens if we start our process to compare two means through the two-sample t-test, and we have a violation of our assumption. Well, if you do, we're going to switch to a non-parametric technique. We've already done this in the past with the one-sample t. You try to do a one-sample t because you want to do a hypothesis test concerning the mean. You have a violation of your assumptions, or the central limit theorem doesn't apply. So what do? You switch to the non-parametric technique that we call the sign test. Well, here we will switch to a technique called the Wilcoxon rank sum, which is applied to two independent samples. Now, our data types. The data types applicable is interval and ratio. Now, just briefly, I will mention that it is possible to do with ordinal data, but for the purpose of this course, we're going to stick with interval and ratio. Introducing the idea, or actually working with ordinal data with this technique, is really outside of the range of this particular level of course. I just want to make you aware of that it is possible to do. Now, the Wilcoxon rank sum is an example of, once again, a non-parametric test. And as you recall, non-parametric tests, one of their biggest strengths is that they're applicable regardless of the distribution. The main strength is that we don't have to have this underlying assumption of normality. The major disadvantage with a non-parametric technique is that it's very conservative. It's kind of like go back to the empirical rule versus Chebyshev's. If the data was mound-shaped, approximately normal, it looks mound-shaped, then we use the empirical rule. Would Chebyshev work? Yeah, Chebyshev would still work on mound-shaped data, but it's not as accurate. You're ignoring, when you use Chebyshev's on mound-shaped data, you're ignoring the fact that it is mound-shaped. Well, if we know it's mound-shaped, we can be much more specific. Well, that's the general theme of most of your non-parametric techniques. The non-parametric techniques are designed to work on a multiple of distributions. Well, if I know I'm working with a very specific distribution, that gives me more information to work with, so I can be a little bit more accurate. So the fact that it's conservative is perhaps one of the most, or the biggest disadvantages to working with non-parametric techniques. Okay, now, this data that I'm about to show you is not the same as what we previously used. Okay, it's the same scenario, but the data has been changed a little bit. Okay, the data I'm going to work with is the furniture data. It's the same scenario we've looked at. The good news is L1, the current technique, that's the same data we used previously. L2, the new technique, that's the data I modified a little bit to help emphasize the point here. Okay, so really, if you already have this data in your calculator, all you need to replace is the new technique. And if you're not familiar with the scenario, take a moment, pause it, read it, or go back and look at the previous examples, because actually the two previous videos I use this scenario with. Okay, we want to start out by using the two-sample t-test. The reason we want to start out with a two-sample t-test is because really we're talking about the means, or at least we want to talk about the means. The assumption is that data is obtained from two independent populations and the distributions of both populations are normal. Now, are these independent of each other? Yes, we've already actually gone through this a couple of times. They are in fact independent. There's two different processes, assembly line processes. There's no connection between them. And when the furniture comes off the assembly lines, we simply take a look at the furniture, and the inspector is going through and noting the number of blemishes. Okay, the normality assumption. Well, this is going to be my current. This is going to be my new technique. I know that we've already done this, but let's go take a look at the normal plots, because the new normal plots will look different. Okay, so I switched to my calculator now. I go to Program, Norm Plot, run the program, option 1. Data is at L1. That's the current technique or the old technique, however you want to phrase it. That's the same normal plot that we looked at earlier. I'm going to just scribble it down quickly here. Good. And then now I'm going to run this program again. L2, this is the new technique. That is a gross violation. So let's switch back to the computer. See, excuse me, I've already drawn the current one in there. This is roughly what the new one looks like. There's issues here. This over here, this gap, I'm not really thrilled with that. There's multiple areas here that concern me, and I'm saying this is not normal. Okay, so if I already wrote out the null and alternative hypothesis regarding the means, I would now switch to the medians. The null hypothesis would be that the median of the old technique is equal to the median of the new technique. Or I could write this as the median of the old minus the median of the new equals 0. They say the same thing. It's just a matter of how you want to write it, which makes more sense to you. The alternative hypothesis, I'm going to list as the median of the old is actually greater than the median of the new. This is suggesting that my new median is less. The new process has resulted in fewer blemishes. And likewise, I can write this as a difference. The median of the old minus the median of the new is going to be greater than 0. Alpha, I'm going to leave it at 0.5. No reason to change it. And then let's go ahead and actually run the program and see what we get. So I'll go back to my calculator, go to Program, and I'm going to go down to the program called Rank Sum. I'm going to run it, and see it tells me I'm doing the Wilcoxon Rank Sum. The alternative hypothesis is the first thing it's asking for here. My alternative is greater than. That's option 3 in this program. So I type in 3, hit enter. Now it wants to know where my data is. Well, going left to right on the alternative hypothesis, left to right on the hypothesis statement, L1, the old data, came first, the current technique. L2 came second, that's the new technique. And just kick back for a second there. Let it do its thing. And it gives you the value of the t-statistic and the p-value. And really what I'm primarily interested in is the p-value. So I'm going to switch back to my computer. I'm going to jot this down. 0.009072. That's what the calculator told me, but really I'm only interested out 4 places. So I'd report it as 0.0090, or maybe I might round and make it 0.0091, whatever. It's not going to make much difference there. It's not going to make any difference, really. With this p-value and this alpha level, the decision will be to reject. And then the conclusion is going to be that there is enough evidence to suggest or indicate, however you want to word it, the new process results in fewer blemishes. So there's our conclusion. Okay, now something else about the Wilcoxon rank sum that you should know about. If you can show the shapes of the distributions are actually similar, then the Wilcoxon rank sum will actually allow us to continue a hypothesis test for the means. So in other words, if we can show that the shapes are similar, the null and the alternative hypothesis, we can leave it as mu1 versus mu2. Now if the shapes are not similar, then we must switch the hypothesis and compare the two medians. which is the theta old. I'm going to make it more generic, not specifically this example. Say theta 1 equals theta 2 versus theta 1. It could be greater than, it could be less than, it could be not equal to theta 2. And again, I could leave these as the mean if the shapes were similar. Well, what do I mean by similar? Well, what I mean by similar is they're both skewed left, or they're both skewed right, or they're both approximately uniform, or they're both bimodal. So if I look at box plots, and that's really the best way to do it, if I look at the box plots and say, yeah, this looks pretty good, they look the same, then I can still talk about the means. Because in reality, I'm going to explain to you why in just a second, but in reality what happens is the Wilcoxon rank sum is actually comparing distributions. So if I say the distributions appear to be similar, and I know that the shapes are the same, well, if it's skewed left, the mean will be to the left of the median for both. So I can still talk about the means. Okay, let's take a look at these distributions and see if we can do that for this data. So I'll switch back to my calculator. And the first thing I'm going to do is, because I know it's here, I'm going to go to y equals and clear out that y naught equals x, because that's the line y equals x. I know it was in my calculator because I just did the normal plot. And every time you run the normal plot, it puts that there, because that's part of the normal plot program. So I'm going to go to stat plot, turn stat plot 1 on, and I'm going to select my box plot with L1. Now I will come up to plot 2, select it, turn it on, make sure I have my box plot selected. I do, with L2. I'll zoom 9 it, and I will get to 2 box plots. Well, looking at this, the first one looks normal. Uniform or normal, one of the two. Well, yeah, we did a normal plot, and it was normal. The second one is definitely skewed right. So no, these do not have the same shape. So for this data, I do need to stay with the medians. Okay, now let's switch back to the computer here for a moment. And I want to just briefly explain to you what Wilcoxon rank sum actually does. It's really kind of slick. Here's the idea. Think of a list for L1. Here's a list for L2. So I have these data in the 2 lists. What Wilcoxon rank sum does is it says, all right, I'm going to take this data, I'm going to combine it into one list. But when I do that, I'm going to remember which list it came from, so I can separate it later. So it's going to put it together. Now it's going to rank the data as if it was one list. So the smallest value amongst those combined lists is going to get a rank of 1. The next value, a rank of 2, all the way down to n1 plus n2. All right, so now the data has been converted to ranks. Now the program says, all right, now that I've done that, I'm going to separate them back out. Okay, you with me? I put data in, ranked it, I separate the ranks. I'm going to put the ranks back out. So now this is what you should expect to happen. If the distributions were the same, shouldn't these ranks kind of intermingle, this kind of intermix with each other? So if I add up the ranks for one of them, that should be very similar to the sum of the ranks for the other. Right? But what if one of them was shifted, one distribution was shifted? Well, then maybe there's going to be a little bit of intermingling or none at all. Well, in that case, if I add up the ranks for the first group, that sum would be less than the second group. So here's the idea. I put them together and I rank 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and it can obviously go on. I'm just going to use 15 from here. Now, if I'm going to use, let's see, group 1 in blue and group 2 in red. If they both were randomly selected from the same population, this is what you expect to see as an example. And this is oversimplified, but I'm putting blue lines under the data that I would expect to see from the first group, and a red line under the ranks for the data that I expect to see from the second group. See how they're just completely, perfectly intermingled, one then the other, one then the other? Now, obviously that would never really happen, but that's what you expect to happen as the purest theoretical sense of it. Now, let's just suppose for a moment that this red group, this one's actually larger. If you look at the number line, it really came from a distribution with a larger median, larger mean. The values are shifted to the right. Then what you expect to see is maybe something that looks more like this. And I actually have no idea. I'm not keeping track of how many of each. Well, here, if I add up the ranks, if I simply add up the ranks, the blue have much lower values, whereas these red ones have much higher values. If I add the red ranks up and I add the blue ranks up, there's going to be a clear separation. The red ranks are clearly bigger. This would correspond to something that looks like perhaps this. I will draw normal curves simply because we've seen them and we understand what that means. Here's a distribution with, say, mean 1, which in theta 1. I drew them normal. Clearly, if it's bell-shaped, or I'm sorry, skewed right, skewed left, then the mean and median is going to separate. But this is just to give you an idea of what's going on. And the second distribution is perhaps up here, with this higher mean and higher median. So this type of scenario would be suggested by ranks that look like this. Now, on the other hand, if both of these came from the same distribution, so here's my blue curve, here's my red curve, it's actually the same distribution, then this scenario would correspond with these ranks. Because clearly if I add those ranks up, the sum will be very similar. The sums will be very similar. Okay, in a nutshell, that's what Wilcoxon rank sum does. It simply it puts the data together, transforms them into ranks, separates them, adds the ranks and says, hey, are these similar or not? And that's it. Okay, that'll wrap it up for what we're going to do with this particular section. Next, I need to switch to the idea of comparing two population proportions. We looked at the means, we looked at the variances, now it's time to take a look at the proportions.